July 1st, 2025. Astronomers spot a new interstellar comet, 3I/Atlas, racing toward our sun. Routine scans until the James Webb Telescope finds a chemical fingerprint that should be impossible. Carbon dioxide dominates, but water is scarce, and somehow nickel vapor shines while iron stays invisible. Could this visitor from deep space force us to rewrite what we know about how worlds are born? Or what else might drift here? The investigation begins with that first breathtaking discovery. Night falls over Mauna Loa Observatory. On July 1st, 2025, the Atlas survey team sifts through a fresh stream of sky data, searching for anything out of place. A faint, fast-moving speck appears in the raw images, just a pixel's worth of light, drifting too quickly to belong to any known asteroid or comet. Within minutes, the team's chat threads light up. Coordinates are double-checked, timestamps verified, and the system's automated alerts ping inboxes around the world. The object is moving at a breakneck pace, over 210,000 kilometers per hour, faster than any familiar wanderer in the solar system. Early calculations show its trajectory is hyperbolic, a slingshot path that will never curve back toward the sun. That's the mathematical signature of an interstellar visitor. Only two such objects have ever been confirmed before: Oumuamua in 2017 and Borisov in 2019. Now, a third, 3I Atlas, is racing through the darkness. As the news spreads, telescopes from Chile to the Canary Islands scramble for a look. Within hours, the Minor Planet Center receives a flood of astrometric positions and brightness reports. Observers compare notes in a flurry of Slack messages and emergency emails. The mood is electric, part disbelief, part adrenaline. Some call it a once-in-a-career moment. Others, remembering the chaos of Oumuamua's brief visit, urge caution and speed. Every minute counts before the comet swings closer to the sun and vanishes from view. Confirmation comes in just 48 hours. The Minor Planet Center issues an official circular. The object's orbit is not bound to the sun. Its path, traced backward, points toward the crowded heart of the Milky Way, near Sagittarius, not far from the galactic center. The designation is formalized: 3I Atlas, the third interstellar object ever tracked in real time. Estimates of its size spark debate. Hubble's first images suggest a nucleus less than a kilometer across, but perhaps as large as 5. It's already shedding a visible coma, gas and dust streaming away in the solar wind. The fact that it's active at such a distance surprises many. Some expected a cold, inert rock. Instead, 3I Atlas arrives with a tail, hinting at a volatile-rich composition and a story written far from our sun. Within the Atlas team, the atmosphere is a mix of exhaustion and awe. One astronomer describes the moment as a shiver, realizing they're witnessing a message from another solar system. The next step is clear: capture its spectrum, decode its chemistry, and figure out what secrets this cosmic outsider carries. With the clock ticking, requests for time on the James Webb Space Telescope and other observatories go out. The race is on to catch every possible clue before 3I Atlas speeds away, never to return. The first spectrum from the James Webb Space Telescope arrives in the early hours of August 6, 2025. On the NARSpec team's internal channel, a hush falls as the data pipeline completes. What appears is not the spectral fingerprint of any familiar comet. Instead, a sharp, broad band at 4.26 microns, carbon dioxide's signature, dominates the chart. The line is strong, persistent, and spatially extended across the coma. In every extraction, from the inner 500 kilometers out to the faint edges, carbon dioxide overwhelms the signal. Water, which usually defines a comet's activity, is present but faint, 8 times weaker than the carbon dioxide. Carbon monoxide, a staple in many outer system comets, barely registers. The numbers are clear. The carbon dioxide to water mixing ratio sits at 8.0, with only minor variation across the coma. For every molecule of water vapor, there are 8 of carbon dioxide. This is not a transient outburst or a trick of the observing geometry. Follow-up spectra taken over the next several weeks confirm the pattern. The composition holds steady as the comet approaches the sun, with less than 15% change in the ratios. Even as sunlight intensifies, water does not surge. Carbon dioxide remains king. The NIR spec reduction team pores over the calibration files, checking for instrument bias or cosmic ray interference. They run the pipeline again, masking out hot pixels and telluric contamination. The result is unchanged. The dominant nu 3 band of carbon dioxide at 4.26 microns towers over the rest. The water nu 3 band at 2.7 microns, usually a mainstay in cometary spectra, is there, just barely. Carbon monoxide's fundamental at 4.7 microns is weak, and OCS is only detected in a few of the brightest fibers. The dust continuum, fitted with a black-body curve, suggests small grains at about 145 Kelvin, but does not obscure the molecular bands. Comparisons begin. No solar system comet has ever shown this ratio at a similar distance from the Sun. Even 2I Borisov, the last interstellar visitor, was rich in water and carbon monoxide. 3I Atlas, by contrast, is a snowball that seems to have forgotten the snow. The chemistry points to a birthplace far from any warm star, perhaps in the cold, UV-bathed outskirts of a distant protoplanetary disk. There, carbon dioxide could freeze out before water, locking in this alien recipe. Laboratory analogs and disk models suggest that only the coldest, darkest environments produce such extreme carbon dioxide dominance. For the NAR spec scientists, the implications are immediate and unsettling. The comet's volatile inventory does not match any solar system archetype. It is neither a typical Jupiter family comet nor an Oort cloud relic. Its molecular fingerprint is a message from elsewhere, written in the chemistry of a world we have never seen. As the team drafts their first summary, the question grows: what else is hiding in this interstellar visitor's coma, and what kind of birthplace could craft such an outlier? The chemical strangeness is only beginning to reveal itself. At the European Southern Observatory, a team pulls up the latest spectra from the Very Large Telescope. The data shows something that shouldn't be possible: sharp emission lines from atomic nickel, standing out in the ultraviolet. In comet science, nickel and iron travel together. Their atoms condense side by side in the same grains, locked in a partnership that survives from the birth of a star system. Yet, in the coma of 3I/Atlas, only nickel appears. The most sensitive searches for iron come up empty. No Fe1 lines above the noise, not even a hint. The team checks their calibration, compares against solar reference spectra, and reruns the reduction pipeline. The nickel lines persist. Iron is missing. This asymmetry is not an artifact. The instruments are tuned to pick up both metals equally. In every known solar system comet, both elements emerge together as sunlight heats the nucleus. Fe/Ni ratios stay close to meteoritic values, a chemical fingerprint as old as the solar system itself. Here, the fingerprint is broken. Nickel vapor floats free, iron remains locked away. Lab experiments offer one clue. In cold, carbon-rich environments, nickel can form volatile compounds, like nickel tetracarbonyl, that evaporate at much lower temperatures than metallic nickel or iron. Iron's own carbonyl is far less stable, breaking apart before it can escape. If 3I/Atlas formed in a region flooded with carbon monoxide and shielded from heat, its nickel could have been trapped in these fragile molecules. Sunlight, striking for the first time in millions of years, splits the bonds and releases nickel into the coma, while iron stays hidden in the dust. For the VLT analysts, the nickel-only vapor is a chemical paradox. No solar system comet has shown such a split. The data suggests an origin shaped by chemistry foreign to our neighborhood, a place where the normal rules of condensation, volatility, and elemental pairing do not apply. The question now is, what other surprises might be lurking in the jets and dust of this interstellar wanderer? A single jet erupts from 3I/Atlas, blasting sunward with the force of a pressurized fire hose. Unlike the gentle, diffuse outflows seen on most comets, this jet is wild, narrow, asymmetric, and pulsing in intensity. Each surge tosses fresh gas and dust into space, carving a lopsided coma that flickers and shifts with every new burst. The jet doesn't just light up the coma, it grabs hold of the comet's spin, acting like a thruster strapped to one side of a tumbling spacecraft. Astronomers tracking the outflow measure its rhythm. Instead of a steady release, the jet pulses in a pattern, sometimes flaring, sometimes fading, but always offset from the nucleus center. These pulses aren't just a spectacle, they're a headache for anyone trying to predict where the comet will go next. Every time the jet fires, it nudges 3I/Atlas off course, forcing trajectory models to be rewritten again and again. What started as a simple hyperbolic path becomes a moving target, with each outgassing event introducing new uncertainty. The physics behind this chaos is rooted in the comet's chemistry. With carbon dioxide as the dominant volatile, the jet erupts at lower temperatures and greater distances from the sun than water-driven activity would allow. The result is a kinetic storm, gas molecules racing away at hundreds of meters per second, dragging dust grains in their wake, spinning the nucleus faster or slower depending on where the jet breaks through the crust. Sometimes, the jet's torque can even flip the comet's orientation, exposing new patches of ice and triggering fresh bursts of activity. For planetary scientists, this is more than a curiosity. The asymmetric jet means even tiny, unpredictable outgassing can send an interstellar object veering off its expected path. Early models that ignored this chaos failed to match reality. The lesson is clear: chemistry and motion are inseparable, and in the case of 3I/Atlas, the fire hose jet is both messenger and engine, turning a simple visitor into a kinetic enigma. Mission analysts gather around real-time displays, watching as 3I/Atlas barrels through the solar system at nearly 130,000 miles per hour, almost 60 kilometers every second. That's fast enough to cross the distance between New York and Los Angeles in under a minute. Its trajectory, plotted against a background of stars, reveals a path slicing in from the direction of Sagittarius, the galaxy's crowded heart. This isn't a gentle visitor, it's a projectile, moving too quickly for the sun's gravity to capture or even meaningfully slow. The numbers on the screen are clear. The closest approach to Earth will be 1.8 astronomical units, or about 167 million miles, nearly twice the distance from Earth to the sun. For planetary defense teams, that distance matters. There's no risk of a collision, no scenario in which this object threatens the planet. The real challenge lies in the unpredictability. Interstellar objects like 3I/Atlas don't follow the familiar patterns of asteroids and comets born in our own system. The combination of extreme speed and unfamiliar chemistry means that every outgassing event, every pulse from its violent jet, can nudge its course in ways models struggle to anticipate. Even a tiny change in velocity, multiplied over millions of miles, can throw off predictions and complicate tracking. The urgency comes not from danger, but from the need to understand. Analysts run simulations, adjusting for the comet's unusual activity and the subtle pushes from its CO2-driven jet. Each update refines the path, but the object's sheer velocity keeps it on a one-way journey out of the solar system. The lesson is clear. While 3I/Atlas poses no threat, its presence is a reminder that the universe can deliver surprises at speeds, and from directions few expect. The focus now shifts to learning everything possible from this fast-moving messenger before it vanishes into the dark. As 3I/Atlas swept into the inner solar system, mission leads at NASA and the European Space Agency found themselves fielding urgent requests from teams across 3 planets. The Mars Reconnaissance Orbiter and Mars Odyssey, already committed to their own science schedules, were pressed into service to monitor dust and charged particles as the comet's coma expanded through the Martian sky. Juno, orbiting Jupiter, adjusted its instrument priorities to capture high-energy particles and dust grains as the interstellar visitor's path crossed the ecliptic. The coordination was anything but routine. Planners juggled narrow observation windows, fought for downlink bandwidth, and rerouted staff to handle the surge in data. One mission manager described the scramble as a stress test. Everyone was running on adrenaline, coffee, and a shared sense of urgency. The Planetary Defense Coordination Office watched closely, treating 3I/Atlas as a live rehearsal for a future, riskier encounter. While the comet posed no threat, its unpredictable jet activity and exotic chemistry provided a rare chance to test the limits of current tracking and modeling. Teams ran rapid orbit calculations, updating predictions as new telemetry arrived, Each pulse from the comet's jet forced analysts to revise their models, exposing gaps in how non-gravitational forces are handled. After-action memos circulated among mission leads, highlighting the need for faster decision trees and better integration of real-time spacecraft data. The lessons were clear. Even a harmless visitor from another star can strain the system, revealing weak points in planetary defense protocols. For the scientists and engineers involved, 3I/Atlas became more than a curiosity. It was a proving ground, sharpening tools and instincts for whatever the galaxy might send next. Speculation swirls, but the scientific teams behind 3I/Atlas keep their focus on the next round of hard evidence. The real breakthrough may come from isotopic ratios, those subtle fingerprints that can reveal where and how a comet's ices were forged. JWST's NIR SPEC and MIRI instruments, along with the Very Large Telescope on the ground, are now targeting the faintest signals, deuterium to hydrogen in water, and the carbon-13 to carbon-12 ratio in carbon dioxide and carbon monoxide. These ratios are the gold standard for tracing a comet's birthplace. If the numbers fall outside the narrow band seen in solar system comets, it could mean 3I/Atlas formed in a region of the galaxy with radically different chemistry, perhaps near the galactic center or in the outskirts of a dying star's disk. But the technical hurdles are steep. The comet's water vapor is weak, making the deuterium lines almost invisible in current spectra. Carbon isotopes are a little more accessible, but require hours of integration and the comet's continued survival as it swings around the sun. No published result exists yet, only the anticipation of what might be found if the instruments catch a break. Lead investigators describe the effort as a race against time and brightness, with each observing window possibly the last. The promise is clear. A single outlier in these ratios could force a rewrite of planetary formation models. For now, the scientific consensus holds firm. Extraordinary claims need extraordinary evidence, and that evidence is still being gathered, one photon at a time. On July 1st, 2025, Atlas identified 3I/Atlas as only the third confirmed interstellar object, and within 48 hours, teams verified its hyperbolic escape from our solar system. JWST's NIR SPEC data showed an unusual carbon dioxide to water ratio of 8:1 and revealed atomic nickel without detectable iron, a pattern not seen in any known comet. High-velocity jets, clocked at over 130,000 miles per hour, complicated trajectory models and highlighted real gaps in our ability to predict the motion of exotic visitors. Despite global headlines, there is no evidence tying 3I/Atlas to artificial origins. Current findings rest on spectral data and established physics. Major questions remain. Why does nickel appear without iron? And what does the comet's composition reveal about other planetary systems? Multiple space probes and telescopes continue to gather data, offering a rare chance to refine planetary defense methods. As 3I/Atlas departs, it leaves behind more questions than answers, reminding us that our understanding of the universe is still shaped by what we can measure and by the mysteries that remain.